Welcome to Sridhari Classes YouTube channel, a learning platform dedicated to build interest, confidence, and strong conceptual understanding in engineering and design subjects. In this video, we explain the theory of the first chapter of engineering mechanics using AI-generated voice and images to make learning clearer and more engaging. Have you ever wondered how engineers make sure that a bridge can safely carry thousands of vehicles or how machines move smoothly without braking? The answer lies in a fundamental engineering subject called applied mechanics. Introduction. What is applied mechanics? Applied mechanics is the foundation of all engineering disciplines. It studies how physical bodies behave when forces act on them. By understanding these principles, engineers are able to design safe structures, reliable machines, vehicles, and efficient mechanical systems. For example, before building a bridge, engineers calculate the forces produced by vehicles, wind, and the weight of the bridge itself to ensure it remains stable and safe. In this way, applied mechanics connects scientific laws of physics with real-world engineering applications. Why mechanics is important in engineering? Mechanics is not just theory. It is a practical engineering tool used in almost every field of engineering. Engineers use mechanics to ensure structural safety, such as determining whether a beam or column can safely support loads. It also helps in machine design, where engineers calculate the forces and power required for machines like engines, cranes, or robotic arms. In fact, mechanics forms the foundation for many advanced subjects, including strength of materials, theory of machines, and fluid mechanics. Another important benefit is predictive analysis. Engineers can predict whether a design may fail before it is built, which saves time, money, and even human lives. Mechanics is the branch of science that studies the conditions of rest or motion of bodies when forces act on them. Engineering mechanics is simply the application of these scientific principles to solve real engineering problems. For example, when engineers calculate the tension in a cable lifting a heavy load, they are applying engineering mechanics. This mechanics is mainly divided into two branches, statics and dynamics. Static deals with bodies that are at rest or moving with constant velocity. In such cases, all forces acting on the body are balanced and the body is said to be in equilibrium. Examples include a parked car or a stationary bridge. Dynamics, on the other hand, deals with bodies in motion when forces are unbalanced. Dynamics is further divided into two parts: kinematics, which studies motion by focusing on position, velocity, and acceleration without considering the forces causing it, and kinetics, which studies how forces produce motion. For example, describing the motion of a train is part of kinematics, while studying how the engine force accelerates the train is part of kinetics. To understand mechanics, we must also understand some fundamental quantities: space, time, and mass. Space refers to the three-dimensional region where bodies exist, often described using coordinates like x, y, and z. Time measures the sequence or duration of events and is essential for analyzing motion. The SI unit of time is the second. Mass represents the amount of matter in a body and also indicates inertia, which is the resistance of a body to changes in motion. For example, a truck requires more force to start moving than a bicycle because it has greater mass and inertia. In mechanics, sometimes we simplify objects to make analysis easier. Particle and body. A particle is a body whose size is so small that its dimensions can be neglected. It can be treated as a point with mass. For example, when studying the motion of a car on a long highway, it can often be treated as a particle. A body, however, is a collection of particles occupying a definite volume of space, such as machines, vehicles, structures, or beams. Bodies can also be classified based on how they respond to forces. Flexible body and rigid body. A flexible body changes its shape or size when a force is applied. Examples include ropes, cables, and rubber bands. A rigid body is one in which the distance between any 2 points remains constant even when forces act on it. Although perfectly rigid bodies do not exist in reality, many solid objects such as steel beams in buildings are assumed to be rigid for engineering calculations. Scalar and vector quantities. In mechanics, physical quantities are classified into scalar quantities and vector quantities. Scalar quantities have only magnitude and unit, but no direction. Examples include mass, time, temperature, volume, and distance. For instance, if one container has 2 kilograms of sand and another has 3 kilograms, the total mass is simply 5 kilograms. Vector quantities, however, have both magnitude and direction. Examples include force, velocity, acceleration, displacement, momentum, and weight. Vectors are usually represented by arrows, where the length of the arrow represents magnitude and the arrowhead represents direction. For example, if a person walks 3 meters east and then 4 meters north, the total distance traveled is 7 meters, a scalar calculation, but vector quantity displacement is 5 meters, not 7 meters, as shown in drawing here, because vector quantities follow vector addition rules. So, applied mechanics is much more than just a subject. It is the scientific language engineers use to understand forces, motion, and the behavior of structures and machines. By mastering these concepts, engineers gain the ability to design the safe and efficient systems that power our modern world. So, these were the basic concepts of applied mechanics, which form the foundation of many engineering subjects. If you found this video helpful, please share it with your friends to spread learning. And don't forget to subscribe to the Sridevi Classes YouTube channel for more such informative engineering videos. Thank you for watching.